говорит, что началось вроде я все правильно сделал. So last time we started our discussion about the depth, and I formulated the following theorem. So let me repeat the theorem. So here I assume that R is in a theory ring. M is a finite R module. And I'm going to assume that I have an ideal such that IM is not equal to M. It's kind of standard assumption when we work with depth and regular sequences. And we have some number, positive number. And so then I have the following four conditions equivalent. So following equivalent. The first condition being that this is conditions about the first three conditions are about the one choice of the x. So xi between n and m is 0, and this is true for any I less than n, for any finite module n, with additional condition that the support of n is inside the line-chain set of the ideal I. So the second condition is just a very special case, the same xi, but now instead of any n with such condition, we choose very specific n, just R module I. So this is the vanishing of any I less than n. And the third condition, just difference in pointers between the first and the third, that the xi between n and m is equal to 0 for any I less than n, and this is for some. And again, finite, of course. This is a statement about finite modules. And for some finite n, and the condition now is that the support of n is equal to the special case of the condition. And finally, now this is condition 4, that there is an m sequence of length n in the ideal R. So, of course, you can see immediately that the sum of the rows are trivial, so 1 clearly implies 2, 2 clearly implies 3. So, also, last time we proved one non-trivial application, so last time 3 plus 4, this is last proof. Okay, so today, the goal for today is to show that the first goal for today is to finish the proof of this theorem and show that 4 implies 1. Okay, remark actually in the proof that in this proof that 4 implies 1, we don't need much of the conditions. We actually can drop some of the conditions. So we don't need in this proof, don't need our theorem or m finite. No, actually, about the second. Well, let's see. Actually, there are more than one proofs. So in one of the proofs, we can prove without these assumptions.
So it's or. We don't need R not trivial or L finite. So it's like взаимоисключающие.
So both conditions can be dropped. Okay, so let's fix the notation. So let's say that x1 up to xn and sequence this is inside I and sequence. So then of course the standard way to work with regular sequences work by induction, so I can look at the short exact sequence. So here I start with the M, X, M, and then M1. Again, this is an independent tradition. If you take quotient by the X1, you call this M1, take quotient by X1, you call this M2, etc. So sometimes you start induction with this X1, sometimes you need to start with X7 and go another direction. Okay, so this is a proof again by induction, and by induction I can say, that the x I between n and m1 is equal to 0, and this is for I less than n minus 1. Right, so in the M1 we have a regular sequence of the length n minus 1, and we have the conclusion 1 for the n minus 1. So then we look at the long exact sequence of x. We have x I minus 1 between n and m1. So then we have x I and M, x I and M. I think that's all I need. Okay, so this map, the last map is induced by multiplication of x1. Now this is 0. So, and this is for I less than M. Okay. So now I want to make the following claim, and this is where we're going to discuss these conditions. Do we need this or do we don't need this? So xi between n and m is annihilated by elements of the annihilator of n. So this is kind of statement that is interesting in its own right. So how you can prove this? Well, I think there is a short and dirty proof. Well, if you want to show that this is annihilated by this thing, for example, you can study the support of this. And you can study support by localization, and then if you know, for example, if you don't drop these assumptions that Aristotle theorem this is finite, first argument n is of course finitely presented, you move the localization inside, and you see that, essentially what you can see that the support, let me say this, if you don't drop this assumption, and more generally let me say that n finitely presented, then support on the xi and an m is equal to the intersections of the supports, just by the localization. Okay? So this is one way to prove it, but actually this statement we can do without the assumption that this is finitely presented, just more or less directly. So let me maybe leave this as an exercise, and maybe we'll do this exercise on the seminar. So you can do this directly by more or less using the definition of x, and just look at the taken element, see how this acts on the resolution. So I want to skip the proof of this part, but postpone this to the seminar. But if you don't drop these assumptions, the proof is quite easy, just this formula. Okay. Now what we need. So yeah, so I want to show one, and I know that the support of the n sits inside the vanishing set of I. Right, so support, of course, for a finite module. Well, wait a second. If I want to say that this is the vanishing set the annihilator of n. For this I need, oh wait, sorry, I confused n and m. N is I want to drop the assumption that m is finite, n is always finite, hence n is always finitely presented, and this works always without dropping this assumption. So, but there's an alternative proof, as I said, without this support by just more or less directly by homological algebra. Now, this proof is less important, so maybe we'll do this on seminar only if you have time. But n is finite, so the support is the same as the vanishing set of the annihilator. Now, if you have this inclusion between the vanishing sets, of course, for the ideals, we have the reverse inclusion.
Why is n always presented?
Because it's finite around theory.
Yeah, but if we didn't drop the theory, if we drop the theory,
Then we
Yeah.
will show it during the seminar.
so
Yeah.
if we don't drop the theorem, but we can drop m is finite, then this solution is working.
Yeah.
Okay.
So m we can drop, but materially we still need to conclude that this is finitely presented, that n is finitely presented. Maybe I just shouldn't drop these conditions and save a lot of time. Yeah, so if you have this inclusion of the vanishing sets, we have the following conclusion, that the I is contained in the radical of the annihilator of n. So what we have? We have that x1 is acting on the xi. Right, so this is module. So xi between n and m. And on one hand, what we proved here, we see that this action, so multiplication on x1 is monomorphism. That is what we proved before. But on the other hand, x1 is in the I, and this is in the radical of the annihilator, right? So it means that some power, so there is, say, some positive L, such that x1 to the L is equal to 0 on the same module, xi, n, and m. So we see that we have an element that x on one hand has a monomorphism, on the other hand it's nilpotent. So that's definitely a contradiction unless this module itself is 0. So xi and m is 0. Okay, so we finished the proof of this theorem, and the first step in developing the next theorem. Okay, so there are no questions. I want to erase this. Okay, so next theorem, and this is fundamental theorem. This is due to Rees again, second Rees theorem. So the assumption says, as before, R is the theorem. M finite R module, but now I have, so as before we have ideal in the R and IM is not equal to the M. So then, under these assumptions, the length of maximal M sequence in I is the following number, infimum of the all i's such that xi between R modulo I and M is not equal to 0. Well, what your previous theorem is not really hard to show this. Well, first of all, we need an induction, so let me put mi to be a quotient of the M modular ideal generated by the first I elements in the sequence times M modular. So is in southern group. So I versus between 1 and n. We have the corresponding short exact sequences. Now, in this case, I want to start with the last exact sequence. So we have mn minus 1, there is xn acting here, and the quotient is n. Now, again, we look at for the short exact sequence, we look at the long exact sequence of x. So here we'll get home. So I'll start with 1 r modulo I, m the index n minus 1. Now this is mapped to the home r modulo I mn. And the next is x1 r modulo I n minus 1.
Isn't it obvious from the theorem? Do we need to make any computations? Do we need to make any computations? Isn't it just obvious from the theorem that we just proved?
Yeah. It's more or less obvious. I'm just trying to explain what is obvious.
Sorry, Casey.
I just don't want to say that it's obvious. Okay, so we have this part of the long exact sequence. Now, by previous theorem, I can say that this is 0, right? Well, actually, we will derive one interesting formula here. During this obvious proof, we will get an interesting formula that might be useful for something else. So this is 0. Now, so here the next map will be map induced by the action of the x1, sorry, not xn, right? But this map is again 0. This is because this is in the annihilator of this module. Xn is in the ideal, hence this annihilates portion by this ideal. So this map is 0. So what we see is that the home between the R modulo I and mn is isomorphic to the x1 I modulo R modulo I m n minus 1. So this, I think, is interesting relation because we can continue this similarly. We'll get the following thing. For example, I now start with the same x1 r modulo I mn minus 1, and this will be isomorphic to the x2 r modulo I, more or less by the same argument, m the index n minus 2, and then I continue this, and the last term is of course xn r modulo I m. So I think this is an interesting observation. Now, so if n is the length of maximal regular sequence, so then by the previous theorem, of course, we can see that this number, this infimum of the i's, such that xi between r modulo I and m is not equal to 0, is at least n, right? This is precisely because the vanishing for the previous x we have by the previous theorem. But now by this formula, so we have together this thing, so let me call this star, starting with home, ending with xn. So by this formula, if star implies the following, that if xn r modulo I m is equal to 0, well, this is the same thing. By this formula, I can go from the x to the home, that home between r modulo I and Mn is equal to 0. These are the same two modules, right? But what it means that this module is it is 0. So if this is 0, again, apply the previous theorem, and we can say that in this case, so by previous theorem, in this case there is an x n plus 1 regular on the Mn. Which is not possible because we choose n to be the length of the maximal sequence. That's a contradiction, and hence this is not just inequality, but this is equality. Yeah, so it's more or less obvious from the previous theorem, but we have one interesting detail of this isomorphism. Okay, now why this Rees theorem is so important? Well, this is because we can give the following definition. So one of the main definitions in this kind of area of mathematics. So the length of a maximal M sequence in some ideal I is called the I depth. This is one terminology, but I prefer to say depth of M in I. And the notation for this, depending what terminology you want to use, is the following. You can say that this is I depth M, or this is precisely the same thing as the depth, but with the two arguments, the ideal and the modular. So why I'm giving the definition after the theorem? Well, because if I just give this theorem, this definition, it is not clear that this is a well-defined notion, right? So it's not clear that any maximum sequence has the same length. But we can compute it completely homologically, and of course that doesn't depend on the regular sequence. So this is well-defined. And another, yeah, so just rewriting what I already have, I can write the following, that the depth I is equal to the infimum of the I x I r modulo I m to 0. So I just want this formula to be on the whiteboard, and this is Rees formula for the depth. So essentially, well, it's not necessarily to start working the depths in terms of the regular sequences. I can just begin my first lecture, say that by definition, the depth is just this number. And this number is actually easy to generalize to some other situations. For example, I can define most of the depths with respect to given ideal, not for a module, but for a complex. I can just as well compute the x between two complexes, replacing by one of the resolutions, and say that this number is the x by definition of complex. Yes.
Does it mean that the depth is a well-behaved and well-defined concept only if we are working in the Noetherian situation?
Yeah. Well, I said essentially all this theory works in the assumption that R is Noetherian. Well, even if some parts of the definition make sense without this assumption, all interesting theorems use theorem of associated primes.
Mm-hmm.
And this usually works nicely on a theory situation.
Okay, and for complex, is there something like length of max M sequence over?
Well, I'm trying to avoid talking about the length of maximum sequence because it's not clear how you can define this. Well, actually, you can, and maybe there are generalization, but sometimes people just use this right-hand side as a starting point of the theory. case, and there is something else I want to see. Just another remark in notation. So if we have the local notation ring, then we use shorter notation, depth R of M, and if I talk about the local ring, it means that the ideal is always the maximal ideal. And sometimes, if the ring is also clear, we can drop this R on the notation, but sometimes we have two rings, so it might be important to put this R in the notation. Okay. So another thing I want to say is that there is a convention that for IM equal to M, we can put the depth of the IM to be by definition infinite. And also, I think part of the convention is to put depth for any ideal and the zero module also to be infinite. Well, it's little exercise that this convention, well, what I mean, this is just the first part. This convention is consistent with Riesel formula. What I mean by this, if you have IM is equal to M, then this happens if and only if all these x are quadratic. Okay. Actually, there will be now more or less series of exercises because I think the proofs are not very hard. I believe everybody can do them. So the next proposition, and this is usually called depth lemma. So as before, R is the theorem. And we have short exact sequence, say 0, U, M, N of finite R-modules. So then we have the following. Well, there is ideal height somewhere hiding in this statement. So then we have three inequalities. The depth of the M is at least the minimum between two numbers. The depth of the U and the depths of the N. This is the first inequality. The second inequality is for the depths of the U. This is again at least the minimum between two numbers, the depth of the M and the depth of the N of the M plus 1. And the last formula for N, the depth of the N is at least minimum of the depth of the U minus 1 and the depth of M. So it's a little bit annoying statement when you write depths everywhere. So probably I should introduce notation D1 to D2, D3 for this depth. But anyway, So the purpose indeed quite elementary. Now to do this, you just take this, shorten the sequence, write the corresponding logic to the sequence, use the reach formula. It's quite straightforward. Okay, and one more proposition, which is again, the proof again will be an exercise, but I think it's a good idea to summarize some basic properties of the Ext in one proposition. So R is Noetherian. We have now two ideals, I and J. So these are two ideals. M is finite. So then we have the following several properties, that if I want to compute the depth of the M, this is the infimum of the depth of the localization for all prime ideals in the vanishing set of the ideal I. The second formula is that the depth is actually more or less geometrical notion, meaning that only depends on the radical of I. Three, which again immediately follows from 2, if you take the depth for the intersection of two ideals, then this is the minimum of the depth with respect to the first ideal and the depth with respect to the second ideal. And finally, 4. So if x1 to xn is M sequence in I, so then we have the following: depth of the I modular this sequence and the second argument is the module modular the submodule, which is a product of the ideal joined by the sequence and the M. So this thing is the same as the depth I and the same quotient module. Again, if you think about this, it's quite an elementary statement. I just wanted to formulate this because, well, if I don't formulate it, I have nothing to think about. And finally, this is the depth of the M minus N. Again, so proof is exercise. Postpone this until for a second. Okay. And now another kind of variation and generalization of the first theorem of today's lecture. So this theorem is again attributed usually to some mathematician, so Ishibek. I'm not completely sure that I pronounced his last name correctly, but this is how I usually pronounce it, Ishibek's theorem. So now I assume that I have Homological theory. I have two finite modules, M and M. Finite are modules. So then in this situation, we have the following vanishing of the x. So xi between n and m is equal to 0 for I less than depth of the M minus the dimension of M. You can see this is generalization because this is local case. What we proved before is just the case like N is R modular singularity. So first of all, let me introduce some short notation. So let me say that the R is dimension M, and K is the depth of M. So the proof is by induction on R. By induction on the dimension. So R equal to 0 means that the support of the modulo M consists just of a maximum ideal M. And so this is first theorem of today's lecture. So the basis of the induction we already have. Now let's assume that R is positive. So we have a prime filtration. Prime filtration of the module M. Now it's just a statement that you have, say, 0 module, let's call this family Xn, that is a module N1, and finally, actually I want this the other one. No, this one. Okay. So a prime filtration is just this finite filtration. It always exists for a finite module over a theory ring. And with the property that if you take a quotient of the nj modulo nj plus 1, and this is always isomorphic to the R modulo ej, where vj is just some prime ideal. If you don't know this statement, we can know quite easily to derive this from the theorem of associated primes. So we will know the statement. So then, if you work intensively, look at the sequence of the short exact sequences, you immediately get the following observation. X, if we have x, let's see, xi and j modulo n j plus 1 comma m is equal to 0 for all j. Then you have xi and m is equal to 0. Just take this notation, write the corresponding short exact sequences. Go with these sequences of x and see that this is true.
Is it in the first x it's n1 quotient by nj?
No, this is nj.
No, nj.
So, using this observation, we can say that so it is enough to show the vanishing of the x I for first argument being just the quotient of the R by some prime ideal. So this is I M. So this is 0 for I less than K minus R. And also we can say that the dimension of the R modulo P is equal to the R. Or, of course, again, if you look at the corresponding short exact sequences, look at the supports, you can immediately see that the dimension of the nj modulo nj plus 1 is definitely no more than the dimension of n. So hence it would be enough to prove this vanishing of x under this assumption that the dimension of the R modulo B is M. Okay, now let's use this condition that R is positive. So if R is positive, meaning that the dimension of the support of n, in this case n is just R modulo B, is more than 0, well, this means that the P that we consider is strictly smaller than the maximal ideal, right? But if this is strictly smaller than the maximal ideal, then there is some x which is in the maximal ideal, but not in this prime ideal P. And I can look at the short exact sequence. 0 r modulo P, multiplication on x, r modulo P. Well, and then there is some quotient which is clearly r modulo ideal generated by the P and the x. Right, so the injectivity here is just because of x, this is domain, so x is not the zero divisor of the domain, so it's injective, and the quotient, well, we just compute the quotient, this is this thing. Now, of course, the dimension of the quotient, since we take a quotient by a regular element on the R modulo P, we can say that the dimension of the quotient is, of course, R minus 1. And by induction, again, this is inductive argument. By induction, we can say that the xi between R modulo P, comma x and m, this is 0 for I less than k minus r plus 1. Okay, then last step for I less than k minus r. Again, we look at the long exact sequence of x. So we have x I r modulo px m. Then we have x I r modulo pm. Then this is map induced by the multiplication of x I r modulo pm, and finally x I plus 1 r modulo dx m. Okay, so these two terms are 0 by the induction.
This I is less or equal than, lesser than k minus r.
Mm-hmm. So we have a module which is xi r modulo pm, and on this module again we have action of the x, and this action of the x kind of give you the same module. So we can write that the xi r modulo pm is the same thing as the x xi r modulo pm, right? But then this x is 0.
Why?
Well, by the Nakayama's lemma. Well, x is in the maximal ideal, right? Remember that general statement of the Nakayama's lemma, if you have m is equal to im, and m is finally generated, and I sits in the radical of the ring, then m is 0. So here the ideal that we consider, this sits in the maximal ideal, which is of course the radical. What was the notation for the radical? This is Jacobson radical, so let's say J of the R. So finally the last thing, let me tell you a story and also use this as an excuse to use some other notation. So instead of writing by Nakayama's lemma, I'm going to write by Nak. This is convention that is used by Matsumura's, and Matsumura's is saying that Nakayama's was quite irritated when the statement was called Nakayama's lemma, so this is for Nakayama, Akizuki, and crew. So, but this is shorter just to write on the blackboard. So writing by Nakayama's lemma, I'm going to write by Nak, and by Nak we have the xi r modulo pm is 0. End of the proof. So this is the proof of the Ishebek's theorem. It has for quite many applications. Well, we're probably, I'm not so sure that we'll see many applications for this course, but if you read some papers, it's quite useful to know this theory. Okay, but one application we'll see immediately right now. So corollary, one important property of the depth. Let me continue with the assumptions. Since this is corollary to a theorem, I'm using the same assumptions as the theorem, and just write formula. So the depth of M is bounded by the dimension of the R modulo E, where E is any prime ideal associated to the module. The proof is now just one line. So if you have a prime ideal associated to this module M, then this implies that the Hom R module B and M is not equal to 0. So just it means that the vanishing of the theorem is not satisfied. It means that we have reverse inequality, and the reverse inequality means that the 0 is more or greater or equal than the depth of the M minus the dimension of the first argument, which is exactly the statement of the corollary. Okay. So the plan for today, I want to prove also the Buchstaben formula. So if I want to finish it before the break, I'll maybe use 5 minutes after the break, but I want to do this proof definitely today. So let me briefly remind you a couple of things that we need to discuss the proof of also the Buchstaben formula. So this is projective dimension. Just a brief reminder to be sure that everybody's on the same page. Terminology maybe bigger. So we have D and phi projective resolution. Projective resolution of M. M is proposing our module. And so then we have P0, so just refer to the M, and then there is P1, etc. So then if I start at some level I minus 1, and now write just the omega I M, where this omega I M is the kernel of the method from the Pi minus 1, which is the differential of I minus 1 to the Pi minus 2. So this is I syzygy of M. Well, just a notation. So you can take projective resolution and cut this projective resolution at the level I. What's left is called by definition syzygy. So you can see that this notion is quite problematic because it's not canonical. You can choose a different resolution, it will be a different module, but if you look at the Shandel's lemma, from the Shandel's lemma, more or less by induction, you can derive that omega I M is well defined up to projective summits. So what we're going to see today also, probably in the next 10 minutes, that there is a fix for this problem in the local algebra. Of the local and theory ring, there is a canonical way to define the syzygy, which doesn't depend on any projective summits. Okay, so maybe definition, projective dimension of M, so notation is noted. Well, there are different notations. I prefer just PD for shortness of projective dimension. So if I need to write R, I write R. R is understood from this. So is the minimal integer such that minimal integer, say n, such that m has a projective resolution has projective resolution of length. So in other words, it stops at n. Well, you can also say this differently. This can be the least integer such that the corresponding syzygy is projective module. That's the same thing. Now, a theorem. Proposition actually. I continue to assume that I have some module, I have always some ring R. Say commutative ring, but for this proposition it's not really important. So the following four conditions are equivalent. Projective dimension of M is less or equal than n. True x n between M and n is equal to 0 for any n greater than d and any module n. 3. Special case x d plus 1 between m and n is equal to 0, again for any module n. And finally, 4. Syzygy with the number d of the module m is a projective module. Okay, well, the proof is really easy. So first of all, that 1 implies 2 and 2 implies 3, this is clear, right? If you have a projective resolution of the length, sorry, this is not n, this is d. Yeah, so if you have a projective resolution which is of the length at most d, then of course if you try to compute with this projective resolution this x, this will be 0, particularly d plus 1x will be 0, and the corresponding syzygy also will be projective. Well, that is just because this is it. At the worst case scenario, this is the last step in the projective situation, or even go further. So this is indeed a very elementary statement. Now, if you go from 3 to 4, this is again quite elementary. If you use the dimension shifting is telling us that the x with the index d plus 1 between m and n is isomorphic to the x with the index. Sorry, the index 1, but first argument is the dth syzygy of the m. So dimension shifting. Again, standard formula from homological algebra. And then with the dimension shifting, well, this is just a characterization of projective modules in terms of the vanishing of the first text. So this again something well known. And finally, 4 implies 1 is again clear. You construct the resolution up to d, and you can see that the last step, the last kernel, is already projected, so we don't need to go any further. Okay, just a brief reminder of the notion of projective dimension, because also in the Buchsbaum formula, we always we get a depth and projective dimension. Now, again, I want to briefly discuss the minimal 3 resolutions. Minimal 3 resolutions. Definition, which is more or less notation. So if M is a finite R module, then the mu of M is the minimal, well then, the the number, so no, the minimal, so the minimal number of generators. The minimal number of generators. So standard notation in primitive algebra. Remark of the definition: if we have a local material ring, then we can compute this minimum number of generators just by computing the dimension over the vector field K of the M modulo MM. So here, of course, K stands for the quotient of the R modulo maximalizing. So this, how to prove this remark? Yeah. Answer is always the answer. Okay. So we can do the following inductive process then. Let's say that by definition beta 0 is the minimum number of generators of M. So then you have a surjective map on the R. Yeah, sorry, I want to say that before I do this procedure, assume that R is local. So I only want to do this for local rings. Doesn't work anymore. Assume that R is local. Then we can use this formula. Okay, so then the inductive process, beta 0, I put this by definition to be just the minimum number of generators of M. And then I have a surjective map from the R to the beta 0. So it's a free module of the ring beta 0.
Not remark, we didn't need the theory there. Yes.
Yeah. That things.
Yeah.
Just
We only need finite module over local rings. So then we have this, and let's put S1 to be the kernel of this map that we just constructed, and then continue doing this. So then I'll put VI to be the minimum number of generators for the SI that I constructed on the previous step, and then I define SI plus 1 to be the kernel of the map from the free module R to the beta I, which is mapped to the SI. So the inductive procedure. So the definition, one of the two possible definitions. So yeah, because I work over local ring being projective and being free is the same. For finitely generated modules, this is easy, so I'm going to use this without saying. So definition, a minimal Fourier resolution of M is a free resolution in which each module has a minimal number of generators. So in particular, we see that the procedure that I described before is precisely procedure that give me a minimal resolution.
yeah, each module
In the resolution.
like each free module.
Yeah, each free module and the resolution. So you can see that on the first step, on the 0 step, I choose the minimum number of generators. I look at the kernel. For the kernel, I do the minimum number of generators, and etc. I just continue doing this.
So like, what if the first projective model will have lesser generators, and the second will have larger? how we... Ну, то есть вот у нас есть как бы две...
No, on each step you just choose the minimum number of generators. So for example, on the first step you could have 1 generator, on the second step you can have 100 generators, so the next step 2 generators.
Mark means that we sort of, I mean, that there is a lexicographical order on,
Yeah, it's...
there is the initial one.
Order? What's the lexicographical?
Ну что, если у нас сначала будет изолента 1-2, а другая изолента будет 2-1? Какая из них меньше? Ну ясно, что 1-2.
Видимо, да.
Если такое получится.
Well, the answer to your question is there's nothing to worry about. The minimal resolution is unique. So you know that any resolution is unique up to homotopy. The point is that this is unique just up to isomorphism of complexes. And essentially this process gives you this explicit inductive construction of this unique resolution. And the fact that this resolution is unique will be on the first assignment. But this is not really a kind of a very hard statement. Yeah, so we have this procedure to construct the minimal resolution, and also we can notice that SI that I constructed are I's syzygy, and by the uniqueness of the minimal resolution, we kind of have this canonical definition of the I's syzygy. They don't depend on the free summons. It's kind of the minimal possible syzygy. Yeah, so if I just introduce notation and I say that Fi is by definition R to the beta I, well then I have 0 as I Fi minus 1, I think. Yeah, I minus 1. 0. Yeah, so another thing to say about the minimal resolution. What if I claim the following? The say the kernel, say of the first map phi 0.
As usual, phi 0 just the commutation map. Then
Next map, I'm going to call phi 1, etc. So this will be phi I minus 1. So kernel of the F0 is contained in the maximal ideal times F0. Could you explain to me why this claim is true?
Could you say it again? What is?
Well, the kernel of this first map is contained in the submodule of F0, which is maximal ideal times F0.
No, probably because when we tensor it with K, we'll get isomorphism.
Yep. And so the answer is more or less again by Nakayama's lemma. So we have this, and then since this was an inductive construction, I can continue doing this and write that the image of the phi I, which is the kernel of the phi I minus 1 by the exactness, sits inside the M times fi minus 1. Okay, so how we can reinterpret this in terms of matrices? So notice these are just all free modules. If I look at any differential here, this is just a matrix of some corresponding signs, which is the beta number and the beta number. I didn't say this. Maybe I need to say this. That the beta I is called I beta number yeah. So we'll get this by induction and what it means for the matrices.
Well, that's coefficients of matrices less than n.
Yeah. So this is equivalent that the coefficients of Fi are in M. And this is kind of the characterizing property of the minimal projective resolution. So you can see that to construct this, we actually use the fact that this is a local ring. And if you try to do this for a non-local ring, there is no such construction. The problem is that if you try to generalize this for more general class of rings, you need the notion something like a projective cover, which is the minimal possible projective module that have a surjective map to the given module. And the existence of such projective covers, they are not true for any ring. They, if this is true, the ring is called perfect, commutative or non-commutative. If this is true only finally generated modules is called semi-perfect. This is kind of different situation. So you can notice that there is this balance between notion of projective and injective, because injective hull exists for over any ring R, but projective cover only for some class of the rings. In commutative world, the most important class of such rings is the, say, local Noetherian rings, but probably you can say just local rings.
Well, projective modules are only local Noetherian rings.
No, I think Noetherian is not important. So there is the more general Kaplanski theorem that I think is saying that over any local ring, any not necessarily finitely generated projective module is free. Yeah, but for us, the most important case will be anyway local Noetherian rings. So the statement is local Noetherian rings are perfect rings. Okay, so now let's derive two more observations about this. What about if the coefficients of the differentials are in M? What can you tell me about the?
About dropping the Noetherian hypothesis, would the kernel still be finite in the Noetherian case?
No, I'm not saying that the construction works. I was just saying that I think you asked a question about the free and projective. So I was saying that free is the same as projective if you drop almost everything. For construction, you need to finitely generate modules.
And Noetherian is.
Noetherian is.
I mean, for the kernel to be finite.
Yeah, you also need this. Yeah. So I was trying to say that if you look at now at the tensor product of this minimal projective resolution and K. So what you can say about the differential? I guess this is a trivial question. So has zero differentials. So in other words, what this complexity is computing, if you look at the homology are precisely the tors, right? So you can say that the tor with the index I for the module M and the module K is isomorphic to the K raised to the power beta I, where beta I is the Bettis number. So that would be another definition, which is also kind of canonical, doesn't depend on anything. You can define the Bettis number as the dimension over K of this tor I. Now, if you do the same computation for the X, I claim that the Hom F K also has zero differential. Do you see why the Hom has zero differential? For the tensor product, it was easy. You just reduce module maximal ideal, O enters and maximal module, so O enters are zero. The Hom is also almost trivial. It's just one crucial step.
Well, the differentials is composition.
So if you say take Fi to the Fi minus 1, right? So then on the Homs you'll get Fi minus 1k Hom Fi k, right? So this would be the map in the complex that in this complex. But what is this map? Here you kind of take a map to the K, right? And then you take this composition. But if this all have O entries in the maximal ideal, and this is map to module maximal ideal, so this composition is zero. So this is a proof that Hom has trivial differential, and the conclusion is the same. X I over R between module M and K is isomorphic to the K to the beta. And that's another way to define basic numbers. You can say that this is
dimension of the x groups. And the second argument is 8. Okay, and finally proposition that I'm going to leave the proof as an exercise. So that Rm, maybe I will do this in the first assignment, be a local Noetherian ring. So M is finite R module. So then we have a resolution. Resolution. So of course, only has the finite resolution. So each I has, well, sorry, not finite means finite, meaning finite project dimension. But I'm trying to say that I consider resolutions such that each of I has finite ring. So if we have this condition as before, that image of the phi I is contained in the M Fi minus 1, then F is the minimal resolution. So in other words, if again all the coefficients of all the matrices of all the differentials are in the maximal ideal, then this is actually minimal resolution. Proof is actually another application of the Nakayama theorem, so exercise. Okay. So it looks like I have 7 minutes left, but at least I start doing this before the break. One of the main theorems in this area, homological methods of commutative algebra. So this is also under Bruce Pavlov as well. So this is for local Noetherian rings. So as before, I assume that R is a local Noetherian ring, and I have M is finite R module. And the key assumption is that the projective dimension of M is finite. So then, projective dimension of M plus the depth of M is equal to the depth of the ring. So it's important to notice that this is not kind of formula that if one side is finite and the other side is finite. Here we need to assume that the projective dimension is finite, otherwise you can conclude this. For example, clearly the right hand side is always finite, but the left hand side is not necessarily finite.
Okay. To prove this, I need a little bit technical lemma, but this is an elementary lemma. So again, this is for local Noetherian rings. Let phi from F to G be a map of finite modules and you also suppose that F is free. And M is an R module. And we have ideal M associated, so M is associated to the M. And phi, tensor product with M, is injective. Then we have two conclusions. So first, phi tensor K is injective.
What is phi tensor M?
I explained this last time. This is standard convention. If I have map times the module, this is map times the identity on this module. So then product with the k is injective. And 2, if additionally, if G is free, then phi is injective, and the image under the map phi of the module F is a direct summand of G. So you'll notice when we prove the Algebra formula that this lemma is a little bit too much. We don't need this full generality in the proof of this formula. But actually there will be other applications of this lemma later. So it makes sense to formulate and prove this in this generality and use this later. And also, since I don't have any special names for this, later I'm going to record this as a lemma before Algebra formula. Okay. So since maximal ideal is associated to the M, we can write the embedding of the residue field K to the M, and let's give this a name I. So F is free immediately implies that product of the F, and so F and I, that's the product of F and I, is also injective. Right? So this is injective. I take it, tensor product with F is free, it's flat, so this is injective. And now the proof is more or less just looking at one commutative square. So we have F tensor K. This is mapped to the F tensor M. This is F tensor I. Now next map is to the G tensor M, and this is tensor product of the phi M. And here the last modulus is G tensor K. So of course these maps are tensor products of phi. Yeah, and this is just a G tensor I. So if you look at this diagram, you can immediately see that this is commutative. Now, what is given to us is that the tensor product of the phi and M is injective, right? So this is injective, and this is injective by the argument before. So this composition is injective, right? So this composition is injective, but it means that this map, the same map, is injective, and hence the first map here in the composition has to be injective. I don't want to write this, but just say that this implies that the phi tensor K is injective. I hope this is clear. Just look at this commutative square. And this finishes the proof of the first part. So let me say this was proof of the first part. Now, the second part,
And we can guess this lemma. 2. So let's write K for the kernel. So F and G. Phi. K is the kernel of phi. And let's take tensor product
with K.
So then we get large K, small k, F, K, G, K. So this is phi tensor K, which is injective by the 1. So 1 implies that the tensor product of the large K and little k is isomorphic to 0, and by NUC, K is isomorphic to 0.
Yeah, and the left, after tensor equals K, the left 0 it shouldn't be here. Like it could be not exact. Like after tensor equals K, it's K is not flat model.
For sure, K is not that module.
So there shouldn't be 0 at at the beginning of exact sequence? Or is it not exact? We didn't claim that it's exact.
Well, it is exact. Now let me return this. Well, then maybe let me erase the 0. Well, if this is not exact, what would be the next term that I need to write in this sequence?
Something like Tor.
Yeah.
But it's like Tor of the co-kernel of phi.
Yeah, but I also know that this is free.
Okay.
So,
Well, it doesn't matter what's standing on the left, because we just say that, no, it's my turn. Yeah, yeah, but it's not short exact sequence. It's
yeah, this is not short, but this is not exact on the right.
yeah. So on the left, it's not a Tor.
On the left, it is a Tor, but this is not a Tor of G.
Yeah, it's Tor of co-kernel.
It is Tor of kernel, yeah.
So Tor of three modules.
Yeah, there's a little argument is missing. You're completely right. So I was trying to clarify this. So modulo this argument, of course, the proof is finished. But we need to say a little bit more. So well, I think what we need is something like this. We need to say that there is an image of phi. Then image of phi is embedded into G. There is this motion by the image of kernel of phi. So you get two short exact sequences. Then you need to write Tor here, which will be the Tor 1 between the image of the phi, right, and k. And by looking at the two short exact sequences, looking at the corresponding log exact sequences of Tors, we can conclude that this is 0.
Well, like it will be something like 0 k f image of phi, short exact sequence 0. Yeah. Well, I'm not sure why it's the Tor 1 of image phi should be 0.
Well, we can try to do the computation. So now let's take a break and we can do some seminar. I think I had a simple argument. This.
Вы в задании семинара в классном, да?
Ну, в принципе, остается видеозапись.
Ну это правда, да. Просто это сейчас... Да, да. Сейчас просто...
Чем ты сейчас?
Сейчас двигаем.
Первая лекция? Первая лекция?
Да.
You don't need to know the proof, of course, you just need to know that there's three ways to define dimension of a module, and there's three ways to insert dimension. I also have a rule class, and I posted my protection also to the Algebra rule class. So that there's no dimension here, but there's the rest. And what I use here is outside the dimension theory, the group is probably those nodes. So if you want to see those nodes, just send an email.
Okay. And can I get these nodes? Do you have something of your own? Like the PDF form or something?
So the nodes that I do PDFs. They are on the rule class. and to get access to visible class. Just a system to manage the assignments. And if you want to take this course for credit, you need to register in the class, because there when you post assignments, you show the assignments and upload photos from the solutions.
Okay, so what are the students?
Send an email and I send you the invitation.
Okay, so I think your official email.
Yeah, Pavlov at HSE.
Yes. I'm going to send an email to myself.
Я вот очень что-то найти по поводу полуортогонального сложения на
Ну, я не что не ставлю, просто думаю, попробовал.
А,
И мне кажется, и даже, кстати, я немножко просто поговорил, у нас тоже просто очевидно, совершенно нечего доказывать. Но я так понимаю, что идея такая, что ну, исключительность просто на формуле Кьюита проверяется. Да, ну, который считает, например, одного произведения.
да, есть.
Вот. А полноту, ну, там надо как-то немножко повозиться.
Вот по полноту, вот, ну, исключительность это да, исключительность это несложно, а вот по полноту.
По полноту там такая идея, что берете этот набор, то есть тест определения набора, да, набор, берете, ну, так, говорите, что пусть надо жить там, или какой-то пучок, в смысле, комплекс пучков программы координации.
Ага.
После этого там опускаете его на один самолет, смотрите, какие у вас получились условия, потом опускаете его на второй самолет,
Ага.
в итоге доказываете, что такое из них не будет. То есть там что-то как очень надо посмотреть. Очень велико, чтобы одна работать. Могу сказать, что точно работает, и что это очевидно.
Но это всегда? Или там какие-то условия надо на X или как положить?
Вроде нет.
Да.
Он сейчас вернулся.
На четвертом.
Кто сюда очень повезет?
Ну, на данный момент Алексей Львович. Через... Да, Алексей Львович говорит, через некоторое время посмотрим. Может, я с Кузнецовым поработаю, но не уверен. Пока что так.
Ну, что такое первое по производной категории, да?
Ну, сейчас пока что моя тема, она более-менее плавающая, но как бы идея, то, что чем я хочу заниматься, это вот разрешением особенностей категории.
Это интересно.
Да, но говорят, это очень сложно. Думаю, посмотрим, насколько я хочу это двигаться. Ну, просто там еще такая проблема, то, что вот типа есть вот, первая статья Кузнецова по этой теме, которая более-менее основная. И она, ну, она там достаточно простая, такая, она не
Я не
сложная.
знаю, как основная, по-моему, основная Кузнецова с Вилсом.
Я как раз хотел про это сказать, что там есть такая, типа, там 2008 где-то статья Кузнецова, она такая открывающая. Потом следующая статья Кузнецова Луцкой, и там уже вот эти даже категории, то есть гладкие категории, вот там это уже как бы немножко накручивается, посложнее.
Там я читал какие-то фрагменты. Но мне кажется, что там все равно Кузнецов очень в целом понятно пишет. У него есть вот эта статья, это уже огромная про аналогическую коллективную производство.
Да.
Вот это вот я не очень люблю.
Я тоже.
Все остальное, за исключением этой статьи, по-моему, как иначе читать.
Да, это правда. Я тоже такое решил почитать. Я ее читаю, и там как бы говорится, ну вот так мы определяем это там хиар, ну там экспрессивная арка, потом это оказывается гарсониана. Что? Почему? Что там буквально просто no set.
Там, по-моему, таких вещей больше отключиться.
Это правда.
Да, кстати, если вы будете все-таки брать эти курсы для оценки, вы зарегистрируетесь в Google классе, пошлите.
Да.
Ну, я вам могу прислать ссылку.
Ну, давай.
Потом останетесь.
Надо, тогда надо...
Да, что уже в следующий пойдет, я первый на вашем разделе хочу выучить.
Ну, такая группа будет создаться. Ну ладно, на тему сделаем.
Есть какой-то проще, согласитесь. Не считать, что можно считать. Надо быстро задушить, что нас запретили, что проблемы недостаточно. Мне кажется, что есть какое-то очевидное нарушение, можно сказать.
Полное Сейчас еще раз, то есть у нас есть это, дополним куда? Коядер или Ага, да. Это
Дело вкладывается в ядро, потому что справа, мы знаем, оно уже индексировано помидорами.
Сейчас у нас там будет ядро f тензор i, вкладывается в ядро g тензор i, вкладывается в ядро коядер, потом в коядро f тензор i.
Просто вот здесь
будет какое-то ядро, да?
Не, вы же вниз хотите, вы вертикальные стрелки. Ну вот комплекс вертикальных стрелок, да ведь?
Нет, я хочу вот это дополнить, написать, здесь какие будут коядра.
Ну просто вот у горизонтальных же тензор i, оно не, ну оно там, у него и ядро, и коядро.
Нет, у него нет ядра, потому что здесь предположение, что уже свободный, поэтому по-прежнему плоский.
Ага, да.
Поэтому здесь нет ядра, здесь есть только ядра, их напишем. Да, соответственно, потом применим лемму о змее, здесь будет какое-то ядро этого отображения. Да, ну, соответственно, оно отображается ядро этого, а ядро этого нулевое.
Сейчас мы и так знаем, что фи тензор К инъективный.
Правда, это мы знаем.
Нам нужно немножко иное. Нам нужно, что фи.
Да. Нет, тогда надо еще подумать. Ну, в любом случае, давайте продолжим. Я закончу это слово. Формула, и потом пишу несколько задач. Okay, so then we have with this lemma, we additionally need proposition, which is maybe interesting again as a separate proposition not related to the depth lemma. So we have local material ring, M as before finite R module. X is an element in the maximal ideal, regular on R and also on M together. So that projective dimension of the module M over R is equal to the projective dimension of the M modulo Xm over the quotient ring by the ideal ring brackets. So the proof, when you have this knowledge about maximal, real resolutions, the proof is quite elementary because, well, you take it.
X is regular on R and on M.
Yeah, together on R and on M. So this is a minimal free resolution. And now using this condition that X is regular on R and on M, and using the proposition that we proved the Homological, there was this kind of first statement of the fortune sequence and the general statement, we can say that this, if I take a tensor product of this exact sequence, I'll still get an exact sequence because this X is regular on every term here. So this is the reason why I need regularity on R and on M. So M, if I have regularity on R, these are all free modules, then X is regular on each of these free modules. That's why I take it as a product is R module X, I still get an exact sequence. So this is exact. But if you look at any of such modules, so Pi, say tensor R module X, then this is the same thing as the R to some beta I as a R modulo X. And this is R modulo X to the beta I. So that's a free module. And moreover, if you have differentials have entries in the M, differentials here also have entries in the M. So in fact, we constructed a minimum free resolution for the quotient module or the quotient free. So that's the end of the proof. So this is minimal free resolution M modulo XM over R modulo X. Okay, so this is all preparation that I need. So finally, proof of the Alexander-Buchsbaum formula. So the proof is by induction on depths. By induction on depth R of the ring. So first case, the base of the induction, so the depth of R is 0. So say D is projective dimension of M. We have minimal free resolution. Okay, so M consists of 0 divisors, right? Because if it has at least one non-zero divisor, then the depth is not 0, but it's at least 1. So M consists of 0 divisors. So M, and we know that the all 0 divisors is the union of the associated primes. Right? So by prime avoidance, M has to be inside one of those primes, but M is maximal, so it's inside. So the conclusion is that the M is associated to R. So by lemma that I didn't completely prove, but I hope I'll give you some correction in the beginning of the next lecture. So by lemma, the last map phi with the index d, so phi d maps PD onto a direct summand of the P with the index d minus 1. But then it means that the projective dimension is actually not d, but this is no more than d minus 1, right? If this last thing is actually by the last map is embedded as a direct summand, we just drop this last part, leave the rest, the complement to this direct summand. This is another free module. So we constructed the resolution which is has length d minus 1. So maybe you can continue this. So definitely projective dimension is no more than d minus 1. So this is contradiction. And from this contradiction, the only way to resolve this contradiction is to say, hence, the projective dimension of the M is 0. Well, but then projective dimension is of this thing is 0, and this means that M is free. Or if this is free and the depth of R is 0, then the depth of M is 0. So the Alexander-Buchsbaum formula means that 0 is equal to 0. Okay, so this is the base of the induction. Now let's consider the case of the positive depth of R. Again, we have kind of two cases here. The depth of M is 0 or not 0. So let's first suppose that the depth of M is 0. So then by the depth lemma, if you apply this to the short exact sequence, we have M, free module P0, and then the first syzygy of M. So by the depth lemma, you see that the depth of the first syzygy of M is equal to 1. And the projective dimension, of course, of the first syzygy is the projective dimension of M minus 1.
Well, on depth lemma, we have Nicole's, isn't it? It's not this depth lemma.
Yeah, on the depth lemma you have an equality, and well, in particular, the kind of how the depth lemma is used in the applications. If you start with the module, you go to the syzygy. If the depth of the syzygy can increase, then the depth is increasing. If this is already maximal, then it's not possible to increase. So we derive this simple observations from the depth lemma. It's more or less immediately for those. So we see that for the depth of the first syzygy, so depth is 1, projective dimension is the same -1. So it means that if I know the statement for the smaller depth, I know the statement for the given depth. So by induction, no, let me say that it is enough. It is enough to prove the formula for the case when the depth of M is positive. The case of the depth of M is 0 can be reduced to this case. Okay, so now the last situation, we have depth of R is positive and depth of M is positive. So this means that M is not associated to R, and M is not associated to M. Right? Now, if this is associated, this means exactly that M consists of 0 divisors. So that's a contradiction. So the M is not associated to the R and to the M. Now, if I use again this observation that the set of okay. Yep, so I can say that M is not a subset of the union of the primes which are associated to the R. Well, this, I guess this is just the same statement. I'm saying that in the M there is an R regular element, so this is not in a set of all 0 divisors. And the same is true for the module. So M is not a subset in the union of all the associated primes. All the associated primes for the module M. So now, again, by prime avoidance, I can say that the M doesn't sit inside the union over all primes which are associated to the R union associated to the M. Okay? I just suppose by contradiction that this sits in this union, then use prime avoidance and get the contradiction. Okay. But this means that there is X in the maximal ideal M regular both on R and also on M.
Now for this element, we can write 3 formulas. Depth of the R modulo X, sorry, of the R modulo X over the R modulo X is depth of the R minus 1. Depth, well, this is since R is X is regular on R. Or the same is true if I replace ring by the module. So this is depth M minus 1. And finally, formula that I proved before, the proof of the Osmanlı formula about projective dimension. Okay, but now, if you use the induction, you can more or less start with the projective dimension over R plus the depth of M. Now, from these three formulas, we express this over ring R modulo X. We assume that this is induction by the depth of the ring, so assume that the formula is correct. Why get the formula for the one dimension less, and you get, okay, maybe I write this, so I get projected dimension R modulo X and modulo X n plus the depth R modulo X plus 1. So then, for these first two terms, I apply the Homological formula for dimension minus 1. So this is depth oil R modulo X over R modulo X, and this is positive. So these two terms together give me this depth by the induction. I have plus 1, and finally the last formula that I use is the first formula. This gives me the depth of R. And this finishes the group of Nelson and Gustav. Now let's solve several problems. And I promised that the first problem for the seminar we will something that I formulated in the first lecture. So consider the case where R, which is a polynomial ring in three variables, x, y, and z. And consider sequence x1 being the product of x and y plus 1, x2 is y, and x3 is e times y minus 1. So then x1, x2, x3 is regular, of course on the ring itself, so but x1, x3, x2 is not regular.
Problem for seminars. This is a seminar.
Yeah.
Will be the seminar.
I just wanted to finish the also a little bit from it.
let's I forgot about this. Maybe we can discuss this as the second question. Give an example. R and M such that projective dimension of M over R is infinite.
We know such examples.
K over K. K is M and R is K of X quotient by X squared.
Yeah. So such an example would be this one. And essentially this always works with the M equal to K if this is some sort of singularity, if this is not a regular ring. Singularity, let's say singularity is something which is not regular. And then this is always has infinite resolution, and this is part of the Serre's theorem that we're going to prove maybe in November, maybe a little bit earlier. And why this works in this example? Well, if you try to construct the projective resolution for this, then of course what the minimal says is try to construct the minimal free resolution. So what's the zeroth bit number? This is just 1, right? So we have this, the beginning. But what are the first syzygy? So what's the kernel?
X. R.
No, I
It's
don't.
like X R, like R multiplied by X.
Yeah,
with
that,
R.
this I think works. So this is the kernel. Well, because yeah, so this is just the quotient by the maximal ideal. This is the maximal ideal. But how we can identify this as a module? So XR is not very clear. What's this as a module?
No, we want to take R and multiply it by X. And it's like
No,
map from R to R multiplied by X.
sure. And what?
This will be
So you want to say that this is R?
yeah.
Well, if you claim that this is R, I don't believe you. Well, okay, yeah, because that would mean that this thing is it's not a zero divisor, but this is a zero divisor. So this is not R, but this is precisely K. As you can see quite easily, well, because in this R x squared is 0, right? So if you have this, what's left is just one-dimensional K vector space generated by the X. So you see that the first syzygy of the K are again isomorphic K. So this kind of resolution is periodic with period 1, and so you do the kind of take the short exact sequences and splice them together infinitely many times. So then the resolution will be something like R, then have multiplication on X, this is K, and then you continue doing this. So infinitely many times. So that's an example of a module with infinite
Free resolution. guy probably started this problem, so we propose this. No.
First of all, times regular, then if times A have no is times F, it means it's not regular. Then we can say that times
You're supposed to use the part with the meat, and your answer, I think it has to be dry.
it's much more difficult thing. Times A minus F is equal to minus F, which means F is something like
Well, maybe just to be sure that everybody understands this, we can write what's happened with this one, where they just Pavlov was right.
yeah, F
So,
is something like
no, you don't need to write that out. I was maybe write sorry, A and F are elements of the homological.
just
Yeah, I think almost clear what we need. We just taking this. Clearly, the first element is trivial because we can talk as zero divisors already. Take the second element and assume that this is second element is y, and we assume that this is a zero divisor modulo this first element.
So why is F equal F should be Y?
y and second we can and that's then means that I put something wrong, but still it's and sorry, I put the wrong thing, but still it's the same. F and they are also co-prime, so it's much easier. And the second step will need it. Now destroy it. And now that the third one is regular, it means
This is trivial.
that's then we can say that A is A times minus 1 times x, which is inside
Like A equal A туш.
просто многочленный множитель на штуку, поэтому это лежит в этом идеале, собственно. Все, что нам доказывает, что это
Ага, да, да.
Now zero means that x is divided by 3 minus 1. Then the e equal to x plus g prime y. And it means that and that's all. Just because a now is not a. F is now equal to I can prove it in the wrong direction. And A is I put this one is that F prime is inside the identity.
Значит, мы то немножко доказали, кажется, да?
Prove that, so we need to prove that the wavelength here is just erase them. So we need to prove that this x is not the divisor on this module. First, I forgot this was these two polynomials, yes? But this is clearly the same module, but I have just to say the isomorphism, that's this module. Because we can just subtract x times y from this polynomial and change them and multiply by -1. Okay, and we can simplify this element because we can subtract the z times y from this element. So essentially what we need to prove that z is not the divisor on r factor xy. But it's obvious in geometrically because it's just a line and z is just a function. It's
Yeah, but I think
doesn't
to
it?
say it's given easily. This is just a polynomial ring in 3 variables. You take a portion by 2 variables.
Yes,
This
just-
polynomial ring in
yes.
1 variable.
It's good. That's
This one variable is not zero divisor.
yes.
Okay.
So what about the statement y x1, x3, x2?
This is okay. So why the so we need to show that times x is Okay, so we have x, then x in this module, and the x3 acts on it, and after multiplication of this element by x3, it is 0. Because, well, this element is clearly inside this ideal.
So yeah, like when we go from that, that y multiplied by y minus 1 is 0 divisor on r quotient by x y minus 1, yeah?
So I can...
That multiplied by y minus 1 is 0 divisor on r quotient
Yes,
by
yes, yes.
x y minus. That's what we
Yes. So,
worked out.
yes, and also maybe a minor point that because in the definition of the M sequence there is a condition that the module factored by all three elements is not 0. But it is quite evident because if just factored by z, we just get k not 0.
Yeah, that's actually quite important remark because at least I personally forget to check this condition. Okay, so this was just an explicit computation, and I think it's important though is from the lecture space look like quite theoretical stuff. But I think it's important to be able to calculate the depths and dimensions and examples. So I'm going to include several such examples in the first assignment. So I think there will be at least 3 or 4 explicitly computing the depths of a given module. Yeah. So, but now I want to give you actually quite elementary problem, and I think maybe you solve this problem on my lectures. But I just want to confront you like this to see these 3 conditions together, and also. Everybody can do this. It's nice to go start with some simple problems, and then maybe next problem will be also simple. So we have a standard situation of the local native ring, and M is finite. Then the following the following are equivalent preconditions. First, depth of M is 0, 2, M consists of 0 divisors on M, and 3, M is associated to M. And just a way to interpret what it means to be maximal to be associated to M. There's not a hard problem. As I mentioned, I think I solved this, but I think it's important to know that these 3 conditions still are equivalent, so we decided to write them together.
Yeah. Okay, so like the first to the second. So to say like okay, depth 0. That means that for any M, that's what it means.
So you need to use this whole part.
Okay. Okay. For any x from small m, x isn't regular only That means that x m not projective. That means that there exists m in M such that xm equal to 0. And that means that x lies in 0 divisors, and that's for any element of maximal ideal.
So if the depth is 0, it means that there are no regular elements. It means that all elements are 0 divisors.
Okay, from the second to the third. M lies in 0 divisors. I understand the problem. So M lies in 0 divisors, that means that that doesn't mean that for one element in M we have M unlike the whole, this element.
No, it means that for any, say, y in the M, there is t in the large M such that yt is equal to 0.
Yeah. That's I didn't finish. Like, well, we know that it's LNR, so
No, maybe you can just use the standard solution of all the 0 divisors as a union.
like as a union of
yeah,
operators. Yeah. Okay, yeah, that's either that's M is equal to E enunciated of M P by prime avoidance. Prime avoidance means that M is equal to P.
Yeah, I think I use this argument
Yeah.
in this lecture.
Okay, and from third to the first, well, when M on associated primes, that means that M equal to annihilator of some x, like exists x in the M large, yeah, and it's M annihilator of it. That means that for any y from there, xy is equal to 0. That means that M multiplication by y not injective. And that means that there is no regular element in M. So the depth is equal to 0. So that means that y is integral. And just any element is integral.
Yeah. Okay, so this was an elementary all this repeating what we already know. I left several properties of the depth as an exercise, and I think the most interesting exercise is this one. So if you want to compute, this is a new problem, if you want to compute the, so okay, let me also do this with now it looks like it is, which is the general statement. So, yeah, so if I want to compute the depth of a modular respect to ideal I can do this by computing the infimum of the depth authorization, and I is updated. I'll formulate this a little bit differently, shortly, but it's the same statement as on the lecture. This is infimum. Not very well written. This is supposed to give you this simple something.
have like finite M and R is not zero.
Yeah, R is not zero, definitely, and M is a finite modulo over R.
So I think we should proceed by using this formula. So let me write it. So the left-hand side of this equation is just into these i's for each x to y factor I and is 0. Okay, what I'm going to use is this. If we are going to look at this x as an R module, so if we take its localization on any prime containing I, it is just the same if we take x of Ri localized at prime P, which we're going to take this P which contain i's, and P. Well, just because localizations are like an exact factor, so it preserves homologies and projective resultants. So, yes, and this is just P. This is just going to be this because E contains this R prime and this.
What is it? It's RP factor.
Localized R
Yeah.
factored by its maximal ideal. Yes. So.
So I still don't understand this.
This is PP, right?
Yes.
Uh-huh.
It's just a residue field. So yes, and so what I want to say.
But how do you get the result?
Yeah, why is it true?
Which one? This or this?
Yeah. Why is error?
Why are you getting maximal ideal here? I think this is the question.
Yeah.
Yeah, I think it's because it contains I.
Yeah, it should be something like IRP. So
Yeah, this P I R. But not yes. That's why it's so.
No, it looks like it's not necessarily maximal ideal, it's just an organization of I and P.
yeah. So that's not zero.
Okay, let's say this.
Yeah.
Okay, yes.
MP it's depth by maximum.
Yeah,
Yeah,
so
yes,
I don't
yes.
find the ideal and I assume this is always maximal.
Okay, let's assume that x, this x without localization is not zero. Then what? Then it is, I think, it's going to be supported on vi because this is supported on I, and if we multiply any this x by any element of I, then it's going to be related. So if it's not zero, then it is some of this localization. It's not going to be to zero. So this is not going to.
Can you repeat why its equalization is not zero?
So localization is not zero because this module is supported on vi, if I'm not mistaken.
Why is it supported on PI?
Because multiplication by any element of I is going to annihilate it.
Yes, but that means that it's like included in support.
Oh
of-
yes, it's supported. It's going to yes.
Okay.
So at any point of this vi is localization on some point p.
Mhm.
Its localization must be non-zero. Therefore, this must be non-zero. Yes. Okay. This is not necessarily maximal ideal. Please, I would like to conclude that x with maximal ideal is not going to be zero. Or something like that, maybe. Maybe.
Now, I guess you can do this. I guess you can do this, but we need to reinterpret this in terms of the regular sequences.
Yes.
It looks like you have something, but in this local case, if you know that you have, say, regular sequence of length n with this ideal ID, right? Then it is contained in the maximal ideal. Then the maximal ideal, you have this sequence and maybe even larger sequences. So you have at least one point.
But wait, in the theorem we needed that, not only that.
Well, you can't explain why there is an
Yeah,
equality.
So I'm just.
Yes.
I would say if you don't have a complete solution, you don't have to make it for the waveform. You can just sit down and maybe work more
Yes.
zero with the neutron. The solution I know actually doesn't use the respawn logic. It's just working directly with regular sequences.
rules I can predict. So, like you said, that you kind of said the proof of inequality. This one. So like if we have a regular sequence here in I sum, and then we localize, we still have the same length of regular sequence in ERP, like in ideal ERP, yeah. And it could be larger if we like it contains in PRP. It could be larger, so that's why it's lesser here. That's clear.
Okay, so you essentially just use this one statement at the beginning of the first lecture that when you localize the regular sequence stays a regular sequence.
Yeah, it was on.
Yeah, so
I suppose some type of this lecture was on the last lecture also. Yeah, okay, and now we need to understand another inequality, and I want to like how I will do it. I want to find some prime ideal that it will be larger, it will be equal. So, sorry, I think you still understand. Okay, yeah, and we have like I is contained in this radical, and yeah, and if we take its radical, its depth should be equal. Yeah.
well, that's another statement.
Yeah, but
We're going to use this.
yeah,
Okay, so let's use it. We can prove the statement also.
yeah, but we stated in lecture, and like.
Yeah, in the lecture, remember there was a statement with two parts, and I suppose we can derive the second part from the first part. This was the first part. Okay, but let's see how this goes anyways.
Ah.
I think it's still interesting.
So, like from this, you want to derive to.
Yeah, because if you know this and you know wrist formula, you can derive that it doesn't have on the particular radical like this. But it's still interesting. So let's suppose that you know that the depth is preserved under taking the radical. How you go here?
I understand. So I probably misunderstood myself, and I'm not sure that I have a solution. Like. Yeah, I want to take some. No, probably.
You're completely right. We need to kind of find the way to find this prime ideal such that the depth of this MP is exactly the same as the depth of M.
Yeah, but that's not a prime ideal, obviously, and that's
Sure. To continue with solution, I think it's, yes, we may not need this, but I think that yes, I was talking about this. So we have ended here, right? Yes, I'm saying that because this localized
Okay.
R
Yeah,
after
okay.
yes this extension, but because we have what? But because we have this, I say
in p squared.
yes. Wait, I think I might be wrong.
Why is it true?
Because
We have it in the p squared.
because it contains I, and so I wanted to say that.
To be honest, I don't even understand the claim, so what's written here?
No, sorry, no, it's all wrong. Sorry,
That's a plan.
sorry for interrupting.
Okay, but I still don't have the proof.
I wanted to say that this has the same support as residual field. So the depth of M with regards to this ideal will be the same with the maximal ideal.
Давайте the support is a reversible field, the support is just the maximal ideal.
Yes,
Maybe
yes.
here, if this is just some ideal, why this has the same support? I don't think this is true.
I suppose, yeah, that is not even true if EP somehow maximum
Yes,
ideal
yes, yes.
maximum.
Yeah, I think you look at some sort of examples, right?
Yes.
Informal variables and procedure.
Можно значит что-то вроде бы взять кольцевой фактор понятно, оно по-прежнему мерцает, и там взять минимальный простой. Их там типа конечное число или это неправда. У нас для них все равно, потому что у нас минимальный простых конечное число это
Это не самое правда, да, это много просто социальный просто с этим, я появился, конечно, число.
Да. Вот. Полыки, если мы возьмем их, то там уже как бы вот, мы когда локализуем, там между и P, ну, и простым идеалом своим, который там максимальный, там нет уже простых.
Ну, можно взять минимальный, да.
Но вот я и говорю, минимальный P фактор P. То есть как бы минимальный содержащий. Ну, мне кажется, тогда это будет право. Сейчас надо немножко добавить.
Скажите, правильно говорю, что так иначе слово вот эта формула особенно условно ничего не будет.
Что это?
Формула условно условно распорол ничего не будет. То есть, я локального разделения схемы, то распорно еще используется. Я помню, что когда я читал про спорт, и там была такая серия утвержденийской математики, которая никак не доказывалась.
Ну там это часто.
Вот в каком-то двусмысленном курсе он закрывает дверь. Дает доказательство секцию утверждений.
Хорошо.
couldn't abstract, so I don't think that we have a solution. It's not time to explain this, so just maybe we'll leave it as it is. So, but I suggest you to try and continue to finish this problem, and I think what you suggested that definitely in the right direction. I think we can go.
Like, for me, right?
Yeah. But maybe not consider the ideal, maybe consider just some ideal generated by massive or something. Yeah, and if you completely stuck and don't know how to solve it, the solution is definitely in the book by Russell Person. Its proposition is exactly the same as list of properties, and this is the first one. So if you start to find it, okay, so that's it for today, and next time we're going to do linear algebra. But not always do, but always do this operator. So essentially we're going to discuss the notion of the array. So let's compare notion of array, so what we do. Essentially one useful notion of array over a weekend. We see how this is related to our properties.